glad you're here. We have this week, exam next week, and then after that, actually, we have a bunch of short weeks. We have Easter break, right? So there's a Friday and a Monday off, and there's only 2 days, the Monday, Wednesday, in the last week. So kind of getting on in terms of the course. We covered a lot of material, and on next Wednesday, we're going to take the second in-class exam, right? And so Monday will be a review day. So we'll read questions, we can look at some study problems, we can look at past homeworks, clarify things. For this exam, you get to have a sheet of notes, right? So you get to have 1 page of paper, you can write on one side of it. You can write whatever you want. You can write formulas, you can write numerical examples, you can write phrases that you think are useful for summarizing a confidence interval or hypothesis test, right? You could use example book problems if you think some are particularly helpful, but whatever you want to put down, you just put it on the page, one side of a normal sheet of paper, and check your calculator that it's working for you. So, right. Today we're going to talk about something called non-parametric tests. There's a whole branch of statistics that deals with what you do when the standard assumptions of procedures don't work. Right. What happens when the data really aren't normal? Or you have a small sample size, or you have outliers. Are you out of luck, or can you actually test something? Can you report something and make a statistical inference? And there are a number of options that are used. Looking at the website, right? So under assignments, under the second exam, some material is posted there. You can have the page of notes. It says there, single-sided. There's an exam from last year that's posted here. Right, this is just the questions. This handout version is just the question, so it's condensed to a couple pages. On the actual exam, it's 6 or 8 pages, something like that. And there was space to write the notes. Yeah.
Is it cumulative?
It focuses on material. There's this handout that's been on the homework since the time of the last exam. So here you go, Ryan. So we really looked at part of chapter 5, there was some normal calculations. We didn't have that on the previous exam, calculating normal probabilities for either a variable or maybe for x bar. Right? Remember x bar, you get sigma over the square root of n for the standard deviation. And then 6, 7, and 8, really. Today we're going to touch on 9, but we're not going to put the sign test on the exam. There's enough material otherwise. And we didn't necessarily cover all the sections of those, so I tried to list out the sections there in this handout, which ones we did. Basically, if you can do those normal calculations, and then we're going to do a confidence interval or hypothesis test, this document here, or a confidence interval or hypothesis test for a mean. We didn't really do it so much with the normal, with the sigma known, but so mostly we moved on to using the sample standard deviation and the t-distribution. We might have matched pairs, and then we're taking differences, but then we have an average difference and a standard deviation of differences, and it looks like a one sample problem again, even though we had 2 measurements per individual. We could do a proportion, a confidence interval hypothesis test for proportion. There were some sample sizes formulas for proportion or for a single mean. And then what we did last time is the difference of 2 means. We're not going to put the sign test, this chapter 9 part, on there, but we'll look at it as an example. It kind of talks about the assumptions. Yep.
So will we be given like those R and T tables, like those?
Yep. The normal and T tables. Yep.
They'll be given to us on
Yep.
the test.
So that'll be a page. Be one on each side. You can take that off, look at it. We're finding those numbers on your study sheet. If you want to write down a few key numbers for the normal, like 1.96 or something like that, you're welcome to do that, but it will be on the table as well. So. Once you do a hypothesis test, usually it's important to interpret it in context, whatever problem you're working on. What does the interval represent? Does it include a key value you're interested in or not? I don't say clearly that I want to do a hypothesis test or a confidence interval, but just say, is it different from something? You can do either one. real hypothesis test about a value, or you make a confidence interval and say that value is either in here or not. Most of the time, I'll do 5% significance, 95% confidence, but if it doesn't say exactly, it's fine to use those as defaults. So that should help get some idea. Again, the homework solutions, probably on Monday, I'll post the homework 8 solutions. We'll try to get graded 8 homework back on Monday. You can write, if you have questions about particular things you're studying, you can email. A suggestion is to write up the study sheet, write up the formulas you think you're going to need, review homeworks and the solutions that are posted. And then based on your page, do you have the formulas you need to do the questions? As you go through some practice questions, if you can read it and say, okay, that has a sample size and a proportion, there's only one of them, it's either asking for a confidence interval hypothesis test, can you identify what type of problem it is, and then look it up on your formula, fill in those numbers, and do it, then that's good. If it's difficult to figure out which formula to use, that's a challenge with this because we've gone over. That's kind of why we pause at this point to try to integrate. There's some things that are about proportion, some things that are about quantitative data and averages. Sometimes there's 1 sample, 2 sample, things like that. The other thing that's on this, right? So this was the exam from 2018. This is the full exam with the tables as it's laid out, so it's a bunch of pages. You don't want to print a bunch of pages. You could print it, and you'd have kind of that to work through. And then these are the solutions to that. And these are some different study questions that I prepared for the class last year. You get the benefit that you get another exam to look at as well. These questions, I had one topic and then presented once as a hypothesis question, and then as confidence interval questions. You can kind of contrast that. There's something with 1 sample or 2 samples. So if you can budget some time for studying this weekend, come with some questions, I think that hopefully you have time to get ready. But any questions at this? Good. All right. Today we're going to look at these non-parametric example test assumptions. And so the idea, when we did a 1 sample test, let's talk about the matched pairs test. We had in observations here, I took a variable x and a variable y, and we measured it on both subjects, the first and the last one. So like in the homework, where there was 10 mothers that were either lactating or post LEP, that the measurements were taken on the same mothers. And so they were correlated. So you want to take a difference. So D1 could be Y1 minus X1, D2 could be Y2 minus X2, Dn Y n minus Xn. And if we look at the difference, if they're kind of roughly, symmetric and not too outlying, and we have a decent sample size, the book, many things will say 30 or 40, but it's really kind of a sliding scale. The more symmetric it is, the less you need. Because really, if it's more skewed, you better average together more things to deal with skewness or outliers. If n is large enough and the DI is not too skewed, without too many outliers, then doing a confidence interval or a hypothesis test, assuming normality, or t, when we're estimating the standard error, works out well. The confidence interval is done that well, 95% of the time, should cover the real thing, the target they're going to, that it's probabilities calculated, like tail areas for p-values. Those should be pretty accurate. Then we would do like a confidence interval, x bar plus or minus p-value with the degrees of freedom times the standard error as a square root of n. And that should work out pretty well for us. Or if we did a hypothesis test about the mean, the average difference, maybe that the average difference is 0 versus an alternative that's not equal to 0. And we take a statistic, x bar minus 0, d bar, sorry. This is a d in this example. And this is the standard deviation of those differences to make it consistent. Right? And then the s of d over the square root of n. And we can compare that thing to a t within minus 1 degrees of freedom and do our hypothesis test based on that. Right? In this is a central limit theorem that the distribution of x bar is roughly normal and bell-shaped. But a lot of studies are done with small sample sizes. Right? If you're in industry and you're testing some big piece of equipment and the testing is going to destroy it, well, that's expensive, right? So they test things like rocket engines of space, and space rockets going to space. Each of those probably cost $10 million, right? They're not going to destroy many of them in testing. They're going to probably destroy a few just to make sure it's working, but they want to limit that. So sample sizes are going to be small, 4, 8, 12, something like that. In my personal experience working with people in speech and hearing, when they're testing children and videotaping them and doing very extensive data collection, they only get in, a couple dozen infants, and that's a typical study. So you have small sample sizes, and if in those small sample sizes you have these big outliers and things, the intervals don't exactly fit the assumption, right? They might be inaccurate for your testing. So what can you do, right? One thing you can do, so if the model assumptions there are questionable, if they're just plainly not met or questionable, right? Then you have to do something else to kind of be believable and convince people, right? Sometimes people transform the data. A square root of x or log of x or something like that. We'll look at a few examples at the end of class of how big a transformation can change the picture so that it doesn't look so much. So if the original data were kind of skewed like this, that after you take the logs of it, the data can often be much closer to a nice symmetric form. And then the impact of outliers and that skewness, you change the question because you're changing the data from the original scale to the log scale. But you can test the average of the log scale and those procedures would work. Right? The other thing is change the question. And by that, we're going to do a hypothesis about a different parameter. A different parameter or characteristic of the distribution. So the first one we're going to look at is we're going to something called the sign test. We're going to make an assumption about the median rather than the mean and see what difference that makes. Okay? The big picture is still the same. Population, and we want to ask something about the population. Instead of asking about the mean, we're going to ask about the median. And then we're going to get data. It's going to be a little bit different than our quantitative data. But then eventually we want to. So if we have a bunch of observations, D1, D2, differences. If there's no difference, one way of talking about there being no difference could be translated into the median of the D's, the D value is 0. So if the median is 0, what percentage of the differences should be above 0? 50%, right? So half and half, right? It doesn't matter what shape the distribution is. It can be really skewed. It can have a massive outlier, right? But 50% median at 0 means half are above and half are below. It's true for all distributions. That's where we get with this thing called non-parametric. It's not an assumption that depends on it being symmetric or normal or anything like that. It's just a fact that the median's at 50%. So the probability, so we're going to have a scenario here where we're going to have maple syrup version A and maple syrup version B. And people are going to rate in raters that are going to judge these. And let's say we get n equals 18 people, and 5 out of 18 prefer A. If they're equal, like we can imagine that they have some quantitative ratings. So let me just jump over, do the quantitative version of it first. So this is this handout that is down here, this one with all the numbers on it, kind of going down a little bit, partway down the page. So if we score a variety A and variety B on a 10-point scale and take the difference, so people score A and they score B. Maybe you randomize which order. Some people taste A first and then they taste B, and other people taste B and then A. So you randomize that. Blinded so they can't see which one it is. Right? And then you take the difference. So a negative is going to mean that A is better. And let's say these are our 1, 2, 3, 4, 5, 6, 7. Okay, that's just 7. It's a little bit different than I had up there. And then 20, I wanted, so there's 18. Well, I was thinking about, right, so these scores here. So this D1 here, right, those D1 values, oops, wrong place. Right. D1 here, those values. And there's this kind of this -8, right? Most people were pretty close, but there's at least this one that's pretty far out there. This is a bigger, D2 is a bigger data set, and so if I continued like that, and let's say maybe sort these in order, so you get all these numbers, -1s to 3s, and there's kind of a -8, a 5 out there. So there's at least one in this small sample. We do a histogram of those. I can't show because it's so small. Let's try it again. So there's this kind of this one that's out there. That's going to kind of distort the sampling distribution because we have a real small sample size. So we could do a t-test here, right? The t-test command, pull this up, right? Compares one sample t-test for those. In this case, there were 20 differences. Right? Get a confidence interval. It ends up being, not statistically significant. P-value 0.05. There's not a significant difference between those. But most people prefer B because it's in the positive. Right? There's -8, there's 4 out of the 20 in this case preferred B, preferred A, right? The other one preferred B. So even though the average is not so different from 0, not significantly different from 0, it is influenced by that big -8 there. Right? That's kind of out of keeping with everything else, that one person. So that one -8, right, the standard deviation of these things is like that. If you take out that one value, if it's greater than -8, take out that one value, the standard deviation is 1.5, but with that value is 2.6. That -8 being out there drives up the standard deviation quite a bit. And although it kind of looks like the distribution's all above, pretty solidly above 0, the significance of it is not statistically significant. So you haven't proven that one syrup, if this is the expensive grade, B is cost more, you haven't really proved that it's worth it. But there's that one point there. Right? But, so if we have so, I don't know how I got 18 and 20, but suppose we had 18 raters, and 5 out of 18 prefer A. Well, under the assumption, under a null hypothesis, that the median right, is 0, then we'd expect 9 differences above 0, and we'd expect 9 differences below 0, assuming no ties. But we only have 5. So in our hypothesis testing, we calculated the tail area, right? The probability you get what you saw or more extreme under the null hypothesis. So we want to calculate, so since it's less, if x is the number, x equals the number who prefer A. So this is the value of D would be less than 0 in that case, the way we're subtracting it. Under this null hypothesis, right, what's the distribution of x? Well, we have n is 18 people doing rating, assuming they're independent of one another. What's the probability of difference, like we said, is below 0 or above 0? It's 1/2. Probability that the difference is less than 0 is just going to be 1/2. So if we have n independent trials, 18 trials, with a probability of 1/2, and they're independent, we're counting, that's a binomial. N is 18 in this case, and D is 1/2. So in hypothesis testing, we calculate the probability we're less than, more extreme than what we got. Right? So we're going to calculate the probability that x is less than or equal to 5, not 18. Based on a binomial distribution, right? And so the nature of these non-parametric tests is once we make this assumption about the median, and we're looking at how many above and how many below, it didn't matter what the distribution of those scores were. Right? We just had a very narrow, very specific, called a sharp null hypothesis. It really specifies everything about the distribution that we need to look at, and it's not sensitive to skewness or outliers or any other funny thing, or sample size. Like that's the distribution. No normal approximation, no large sample thing going on, and we can do that testing. So if you do that, that's the first part of this handout. So this thing, so if we had 5 out of 18 prefer A, the probability they prefer A is 1/2, median score at 0. The probability of 0 is this density calculation here, that's the binomial density out of 18, probability 0.5. With 0, 1, 2, 3, 4, 5. These would be all the separate probabilities, and this would be the sum from 0 to 5 of that tail area. So the chance that you would get 0 out of 18, when it's really 50%, is practically 0. It's just not going to happen. Or even 1, right, if you do the next one. This scientific notation means 0.00006, 8. Very, very small chance. 3, 2, 3, 4. There's a little bit of chance of 4, kind of a 3% chance of 5. That's all 5 of them, all 6 of those numbers together. And if you add them up, there's a 0.48% you'd get 5 or less. 0.048 chance that you would get 5 or less. So in this case, we had 18, this calculation. We saw 5, where 5 cases have the DI is less than 0, which means that A is better. And we're going to calculate the probability that our X is less than or equal to 5. So what was done here is sort of taking the numbers 0 to 5 and calculating the probability that we have that number. And it's actually the binomial formula. There's 18, choose X. And P is 1/2, so it's 1/2 to 18 all the time. But that ends up being 0.048. So we actually get a probability right there. But that's kind of small, but If our two-sided alternative is we don't care if it's smaller or bigger, it's all symmetric, what we're going to report for a p-value is 2 times that, 2 times the tail area of 0.096. And I remember our null hypotheses, we said that the median difference is 0 versus an alternative that the median is not equal to 0. Does this evidence convince you that variety B is significantly better? What do you conclude generally with p-values that are this size?
Because it's greater than 0.05, the number is
Actually, it goes the other way, right?
Oh, it goes the other way?
Yeah. So small p-values, right, are going to be far out in the tails. Right,
So there's really not much difference.
yeah. So this is greater than typical cutoffs, 0.005. Right? So we don't reject. Right, it would seem to fail to really be convincing based on these 18 people that it's significantly different than 0. So we don't reject hypothesis. Conclusion. Right, the syrups, the 2 main triple syrups, are not significantly different. You can think about what would happen if we had even fewer people preferring A and giving, negative differences there. Right? If you only had, not 0. If we had only 4 people out of 18, right? The tail area, the chance that you're more than that would be 0.015. Right? And we doubled that, we'd get 3%, and that would be significant. Or even just 3 people out of 18, right? That it's really imbalanced, and there's a very, very small probability we would get, that would happen if it's truly 1/2. Right? There's in R something called a binomial test, where you put in the sample size, the number of trials of 18, and the number that you got, and it does this calculation exactly. It says, is the true probability 0.5? Right? Is it, that would be the median being at 0, half the difference is below, half above. There's a confidence interval for that proportion. 5 out of 18 is about 0.28, and it gives this p-value that is not small. So you wouldn't reject, right? The whole point of doing this is that, with a real small sample size, if you have one of those outliers or a few outliers or some skewness, it might not be all that convincing to state something based on the t-test. Now, if you had bigger sample sizes, right? So if you had 25 out of 70, now 25 out of 70 isn't even quite as extreme, right? 25 out of 70 is 0.35. So that point estimate, the estimate of the probability of preferring A, is about 36%. It's a little bit closer, but it's based on a bigger sample size. So could it be significant? If you do the binomial test with that one, you get a p-value here that's actually smaller. So that's not as extreme away from 50-50, but it's a bigger sample size. So it is significant. So you test 70 people and you get something in balance like this, 36% favor A, 60, whatever it is, 63%, 64% favor B. That looks like it's not 50-50 or more. So again, going back to this, if you had, the data, or this data, if you do a t-test based on this one, this t-test, like we saw here with these data, was not quite significant, right? So the t-test is about the average. And the standard deviation plays a big role there. Right? That big outlier makes it, the standard deviation bigger, as we make the standard error bigger, make this confidence interval wider, right, because of this 1 point sticking way out there. So it's not significant. Right? You need to claim that this is significantly better to market it, right? This is not going to help you. However, what about our sign test, this median test in this case? The median of these is actually 2. Not that we had to know that exactly. But out of these, let's sort the D2 values. Out of this 18, 19, 20 of them, right, just 4 are negative. Only 4 out of 20 people preferred A right there. And the binomial test, if you run that, does give you a p-value that's a lot less than 0.05. So a test for median, in this case, is pretty conclusive that the median score is bigger than 0. It's, there is a strong preference for B over A. It is significant. But if you do it based on the mean with that outlier distorting things, it didn't quite pass the test. Now, in terms of honest communication, I think it's good to present both, whatever test you do, and tell people the results of both. Show them that graph. This one caused the first one to not be significant, but the sign test, this median test, is significant. And then let them deal with that. Right? You could make a legitimate claim that I believe the median test more than that one because I think that was kind of an oddball answer, that this is typically very unusual for that pattern. Like most people would think that it's good, right? So one other example in biology. So Sokol and Rolf in their book on biometry have an example where they have 2 different strains of guinea pigs. They've been growing in labs for over 9 years. Somebody that studies a certain insect or thinks has a room full of ants or a room full of spiders or a room full of guinea pigs and studies them. And they have 2 strains of guinea pigs. Maybe these are out in the field or in a zoo or someplace. And how many babies do they have in a typical year? They take the average difference over 9 years. So these are small numbers, but if different litters have these are matched up by places that they're living, they're growing, living together. These 2 different strains under certain circumstances, they're matched. I don't remember exactly how, but different labs are growing different groups. And so if you had, say, 9 years, if one had 20 babies and the other one had, so one had 18 babies and the other one had 9. Over that would be a difference of 9, and you divide that by 9 years. It's an average of 1 per year. These numbers are a little bit smaller than that, but you're getting something on that magnitude. These are the differences between matched pairs. The average is about 0.1. The median is about 0.09. Here's a histogram of those. This one has kind of an outlying pair up there. If you do the t-test of this one, well, I guess it does get a significant p-value. Standard deviation's big enough. Now, out of these differences that were in there, there's only one, and only one pair of these 2 different types of guinea pigs. Was it a negative difference? Right? So it's only 8 out of 9. And so if you do that, 8 out of 9, you still get a significant difference here, right? And this kind of helps you. So you've done it 2 ways. They're both significant. One is sensitive to assumptions, and the other one's not so sensitive. But any questions about it? So again, we won't ask you specifically about this particular test. Some of the logic of hypothesis tests, like setting up a hypothesis, looking at how extreme the values are under the null hypothesis, getting a p-value, deciding if it's small or not, are still relevant. The other kind of non-parametric ones that you would see in study if you go on, particularly to a second course in statistics, a number of these things are based on ranks. We have a bunch of data, D1, D2, Dn, and you put them in ascending order and say what rank is each, which is the smallest, which is the second, and so on. The ranks for n observations is just one through n. It doesn't have a big outlier on either side. It's uniform. It's one to n. Right? So it's kind of free from that. And we have kind of 0 somewhere here in the middle, and we have some points over here that are less, and some points over here that are more. So sometimes these non-parametric, we make different assumptions about characteristics. If this is symmetric, about 0. 0 is in the middle, and it's kind of symmetric. You might have outliers, might be extreme, might be non-normal, right? But if it's symmetric about 0, then the positive differences and the negative differences should be quite comparable in their magnitude. That means the absolute values of the DIs, you take the absolute differences here. It'd be like folding these over there. And then the idea behind these procedures is you take the ranks of those, ranks of these absolute differences here. So you fold them over and then rank them. Some are close to 0, so they're going to be all small ranks. The ones that are out in the tails are going to be big ranks. If the distribution is symmetric, about 0, about 0, then the sum of the ranks of the absolute differences should be about the same for the ones that are coming from this side or the ones coming from that side. And so this ranked procedure, we're not going to go into all the details. It's in the book. It's referenced and explained in the book. Sometimes it's called the Wilcoxon rank sum procedure. But because of the nature of the ranks, that if you have a certain number on one side and a certain number on the other, and it's really kind of uniform in the ranks, you can figure out how the it's a combinatorial probability problem to figure out what's the chance that it would be bigger than one side or the other. It can be kind of simulated. So the short story of it is you can do this complicated thing that doesn't depend on the actual distribution of the D's and still come up with a p-value. Get a test statistic and a p-value for testing. Is it symmetric or not, right? So I test the hypothesis. Are they symmetric about 0? Versus an alternative not symmetric. And so you do a test statistic, evaluate that, get a p-value, with the p-value small. We're going to reject null hypothesis. And conclude that it's imbalanced to one side versus the other. So we haven't got through all the details actually calculating that or with an example. It's just pointing out that there's other ways to set up hypothesis tests. And except for the details of doing the test, the same overall logic is there. So if we look at R, there's a test called Wilcox test. In R, it doesn't have as many assumptions as the binomial test. It's a little more powerful than the binomial test. I mean, it doesn't have as many assumptions as the t-test, rather. If you look at the ranks, there's a total ranks, and if half of them, that's kind of on theirs, the n times n plus 1 over 4 should be associated with one absolute ranks on one side versus the other, and you can get a statistic. So remember our values of D, these were our things here. They're mostly, I don't know, are they mostly positive? But yeah, they're mostly positive. There's just a few here. If you run that test, all it gives you, details the Wilcox sign rank test, data, it gives you some statistic. It adds up the ranks on, the absolute ranks on one side. That's what that number is there. But then it gives you a p-value. So in this case, right, if we put an AB line and a vertical line at 0, red to stick out, most of the differences are on the positive side. So most of the ranks add up on the positive side. It's a lot bigger than average. So you get a very small p-value when it evaluates. So this would be a significant result, that one strain is significantly different than the others. So anyway, that's another type of test that's there, and these are some details about doing it. Last thing I'll show you is that, what does the transformation do? So there's a bunch of data sets that are available in R. There's a big list of different data sets that are used as examples of things. One of those is islands. These things all have help files, so help islands. Areas of the world's major land masses. Thousands that exceed 10,000 square miles. So, but if you look at the histogram of those, some are, massive, right? And then there's some that are mostly small, extremely skewed. If you try to take a sample of these and then do a t-test or something from data that would be like this, the sampling distribution won't be symmetric and it won't work out so well. But if you take logs of those, it's still skewed because the original was just so skewed, but it's not nearly as bad. Right? Kind of pulled it back in. So a sample from this, it still might be a little bit questionable, might be better. Here's a histogram of river lengths in the United States. So what are some of the biggest rivers and the longest rivers in the United States? Mississippi. What else? Any others? Missouri, Colorado, some big rivers out in the Midwest. Yeah. So, right. But few of them are more than 1,000 miles long. Right? But that's pretty skewed. If you take the log of that, on the log scale, it's much more symmetric. So sometimes we'll do that. This is a data set on states. And so there's the 50 states. Here's a histogram of populations by state from a few years back, 1977. So yeah, it's getting a little bit dated. Right. What are some of the big states in terms of population? California, New York, Florida. Right? Some of the small ones like Vermont are back down in here. Right? So 5 million, we're not even close to that. But that's very skewed, right? You can take the square root of population or his log of population on that log scale. It's, the log is looking at what exponent is in there. Is it 10 squared, 10 cubed, and so on. It's on there more. Or area of states. And what's the state that has the biggest area?
Alaska.
Alaska, and Texas, and Pennsylvania I think is pretty big. So California. But the square root of the area is what's kind of a funny shape, but it's more not as skewed. And the log, again, there's a lot that are concentrated in a little narrow area. It has kind of long tails, extremes out there, but it's, you can look through different examples. So if the data, if you're doing a t-test with small sample sizes, I think it's just imperative to look at the data, see what it looks like. You learn a lot about it. You learn if you have big errors. I use graphs all the time when I'm programming or something and I think I'm going to get some output. I look at it graphically and then find out where I made error. Just immensely helpful. And in this, some of the assumptions, we want the sampling distribution to be normal. Small sample sizes, skewness, outliers is going to kind of mess that up. If you're ever in that situation, you can consider some of these non-parametric alternatives or transformation for some things. That's about it for today. We'll do review on Monday. If you haven't handed in the homework, you should have dropped it off.
We're like,
Yeah,
really
yeah, I'm
happy
like-
up, and she's like, okay. No. Have a good weekend.
Thank you. Yep.
Have a good weekend. Huh?
I don't, you can just put it in there, we'll put it together.
Can you just go over how to like find p-value for me real quick, please?
For
Just
some,
like, yeah, like what the one, like even just like the ones that we were just looking at, like you have the p-value and you have 2 times.
yeah, so this one, this is a tail area, right? So
Yep.
the outcomes go from 0 to 18. We observe 5. So we're gonna look at 5 or less. So 0, 0 to 5.
Mm-hmm.
This is adding up the probabilities we've done in that tail. And because we're doing a two-sided test, right, very small values and very large values would be kind of equal evidence against that, so we just double it. And that's the p-value.
So then, so it's just 2 times
The tail area
tail area.
for a two-sided test.
I know from myself and we were talking earlier,
Yeah.
we haven't been able to finish the homework yet.
Okay.
We were just wondering if we could hand it in like on Monday.
Okay.
Yeah, I'm
Yep.
kind of having the same problem.
Okay.
Yeah, okay, yeah, sorry.
No, you guys can have it sent until Monday.
Thank you.
Okay, thank you so much.
Thanks.
Yep.
We'll have questions for the test on Monday too.
Okay.
Thank you so much.
Yep, yep. Well, it helps when everybody, you know, when you're attending in good standing from the course, it's easy to get, you know, real leniency, so.
Yeah. We were trying to do it together and there were some.
Okay, if you have questions over the weekend, you can send emails.
Okay.
and I'll try to
Awesome.
Thank you, appreciate it.
respond.
Thank you.
Yep.